Consider denoising data on a surface. This is usually done with a smoothness energy. Previous methods work well on closed surfaces without boundaries. If the surface has boundaries, however, problems occur. The isolines are biased by the boundary. The standard energy used for smoothing employs low-order boundary conditions. In our paper, we solved this problem by minimizing a similar energy that naturally includes higher-order boundary conditions. We call it the squared Hessian energy. Notice how the standard method forces the function's isolines to be perpendicular to the boundary, while our method does not. The energy we propose has several advantageous properties. Far away from the boundary, it behaves very similarly to the standard method. Only at the boundary does the behavior of the squared Hessian energy differ. The squared Hessian energy smooths our function under the assumption that it is locally linear near the boundary. Functions that measure zero energy are entirely linear. In contrast, standard methods prefer the function to be flat at the boundary. Functions that make the standard energy zero are entirely constant. Naively ignoring the boundary contributions for the standard energy leads to no denoising at the boundary at all. The squared Hessian energy can be used anywhere in geometry processing where a smoothness energy is required that should ignore the boundary. Interpolating with the standard energy gives results that are heavily dependent on the position and shape of holes in the domain. If these represent noise, this is unwanted behavior. Our squared Hessian energy avoids these issues. If we try to address this problem by smoothing in 3D, simply ignoring the geometry, we get massive overshooting. The squared Hessian energy still exhibits the shape-aware properties of standard energies, while at the same time being boundary agnostic, like simply smoothing in 3D. A special case of scatter data interpolation is handle-based character animation. In this case, we are interpolating displacement at the handles. Previous methods built discrete energies not based on known continuous energies. This can lead to discrete error in the result not accounted for by any continuous theory. This causes instabilities in the result. Correctly accounting for the smooth theory leads to more natural results. Using the squared Hessian energy to define linear blend skinning weights allows us to ignore holes due to missing information. As another novel application, we consider minimizing our energy under an L1 norm instead of an L2 norm. Notice that the L1 norm concentrates non-smoothness along creases. The L1 norm applied to the standard energy concentrates the error at isolated points, leading to a spiky appearance. The L1 norm of the Hessian creates piecewise planar shapes by concentrating the error on creases. We can also use the L1 norm to smooth the geometry of the surface itself, leading to piecewise smooth flows. In conclusion, we present a novel smoothness energy that is boundary agnostic. It can be used for many geometry processing applications where smoothing energies are used and will ignore boundaries better than standard energies. Please refer to the paper for the theory behind natural boundary conditions, the biharmonic equation, and interesting math by Courant and Hilbert. Thank you for watching.